Hey kids, this is Mr. Polino. I'm going to take care of the basics for section 2.7, operations on functions for you. You saw about half of this in your Algebra 2 classes previously. Basically the mechanics of it, you could calculate with it, find answers. The pre-calculus slant on it will be to look more about finding domains and ranges, as well as the applied problems and how these would look in terms of being able to write these from word problems. Let's take a moment here, take a look at the list of things to know, list of things to do. Remember that our essential questions, what are the basic and general algebraic and graphic characteristics of functions that can be applied to a wide range of mathematical equations. We're almost done with this chapter. Once we get into chapters 3, 4, and past, we will be applying the ideas, concepts, and skills from this chapter for basically the rest of the year. So we want to have a really good grasp of them. For things that we should know, the definitions of sum, difference, product, and quotient of functions, and the definition of composite functions. That's, as you recall, your f of g of x sort of stuff. You probably already know those, but we just want to make sure. A little more interest probably what we should be able to do. We should be able to find the sum, difference, product, quotient, and composition values given specific inputs. That is, if we're given a specific value for x. Find the sum, difference, product, quotient, and composition of functions to write new functions, where we're just composing functions to write new ones without any actual numeric values for the inputs. The third bulleted item, find the domains of the operations on functions. That's going to be definitely something that is new. I don't think we've done that in the past. And then use operations on functions to write functions from real-world situations. And that's where we're going to do that. The last bulleted item, which is kind of a carryover through all sections, you'll see that's probably at the bottom of every list of things to know and things to do, is be able to solve applied problems that involve the topics above. So that's where we're going to work for through today. Remember from your Algebra 2 days that the sum, difference, and product functions of quotients is, if we're given the two functions that we're going to add together, f plus g of x, we can rewrite that as f of x plus g of x. Please do not confuse this with the distributive property. It is not the distributive property. The distributive property applies to multiplication. This is input functions. These are f plus g of x, not f plus g times x. But this is how the definition works. So we have f plus g of x equal to f of x plus g of x. Similarly, for the difference, f minus g of x is equal to f of x minus g of x. And the product of functions, f times g of x equals f of x times g of x. I did not put a operational symbol between the f of x times the g of x, but you could just as easily write f of x times g of x, and that would be no big deal. We've seen those before. We've calculated with those before. The new slant we're going to put on here is, well, what are the domains of functions when we start putting them together? And the answer is, the domain for any of the function operations above is the intersection of the individual domains of f and g. We have previously in this chapter looked at how to find the domain of a function algebraically. And so all we would need to do is find the domain of f. So you would find the domain of f. You would then find the domain of g. And you would see where they intersect. Remember, intersect is basically where do the values for those, what are the overlaps for those two individual domains. So that will probably be the new part of this for you. So that is add, subtract, and multiply those. Why isn't divide on here? Because divide is slightly different. So for the quotient of functions, the definition looks the same. F divided by g of x is equal to f of x divided by g of x, with one little restriction, provided that g of x does not equal 0. Obviously, if g of x did equal 0, we'd have a 0 in the denominator, and we would have some trouble, and we would not be able to use that particular value, which is why the domain changes slightly. The domain of a quotient of functions is the intersection of the domains of f and g, just like it was before, except we have to throw out where g of x equals 0. Well, my formatting is not great there. Let me see if I can fix that. Hang on. There we go. A little better formatting there. Where g of x equals 0, since we cannot allow for a 0 in the denominator. G of x equaling 0 is fine if we're adding, because we can add 0. It's fine if we're subtracting, because we can subtract 0. And it's fine for multiplication, because we can multiply by 0. However, if g of x equals 0 with a division, we do end up in some trouble. So whatever value of x, whatever value we'd put in here for that x, cannot produce a solution of 0, only for division. Everywhere else, okay, just division would not be good for us. All right, let's take a look at some examples here. So example 1, f of x equals 3x minus 2, g of x equals x cubed. Find these 4 particular values. So f of g plus 2 would be, following my definition, f of 2 plus g of 2. And f of 2 would be 3 times 2 minus 2. And g of 2 would be 2 cubed. And you'll note that I grouped them together because I want to make sure that I do not have any sign errors. My first set of brackets will be 6 minus 2, which is 4, plus 2 cubed, which is 8, and I get 12. So f plus g of 2 equals 12. What I just did there was the first bulleted item from your list of things to know, which was be able to evaluate operations on functions with a specific value. I had a specific value, x equals 2. And I'll go through and do some for the same for subtraction, multiplication, and division. So f minus g of 1 would be f of 1 minus g of 1, which would be for us 3 times 1 minus 2 minus 1 cubed. So that would be 3 minus 2 after I do that. 3 minus 2 is 1. 1 minus 1 equals 0. So f of g minus 1 is equal to 0. Please pay attention not only to the solution, but the structure and the notation of the way these problems get written. Thank you. F times g of a half. So that would be f of 1/2 times g of 1/2. F of 1/2 would be 3 times a half minus 2 times 1/2 cubed. Well, 3 times a half is 3 halves. 3 halves minus 2, that's really 3 halves minus 4 halves, so that's negative 1/2. And I'm going to multiply that by 1/8. 1/2 cubed is 1/8. And that will give us a negative 1/16. So f times g of a half is 1/16. And for our final example with specific inputs, f divided by g of negative 2 would be f of negative 2 divided by g of negative 2. F of negative 2 would be 3 times negative 2 minus 2 over negative 2 cubed. My numerator, I'm going to run out of room here. My numerator is going to become negative 6 minus 2, which is negative 8. And negative 2 cubed is also negative 8, giving us 1. So f divided by g of negative 2 is positive 1. That is how you simply find and evaluate operations on functions for a specific value. Going back to my no-do list, that's what we just looked at right there. We haven't taken care of composition yet, but we did it for a specific input. So on the list of things to know and do, that's what I mean by a specific input. For our second example, we're going to go in a more general case. We don't have a specific input. We have the function f of x equals the square root of 4 minus x squared, and g of x equals 3x plus 1. We're going to find the following functions and state their domains. I'm going to slide that out of the way, give myself a little more room. So f plus g of x, I don't have a specific input. So all I can do is apply the definition and make it f of x plus g of x, which becomes f of x being the square root of 4 minus x squared plus g of x being 3x plus 1. Now, as I look at it, there's not a whole lot I can do to simplify that. I don't have any like terms. I don't have anything that I can reduce or cancel. So that actually is going to be my final solution for the function. It's not the prettiest one in the world, but it is what it is, and we'll just leave it like that. So that is the final definition there. In terms of finding the domain, remember that to find the domain, we're going to find the individual domains. We're going to start by finding the domain of f. Then we're going to find the domain of g. We'll see where they overlap. So my domain of f, I'm going to label my work. I have a radical here, so I have to make sure that 4 minus x squared is greater than or equal to 0, which means 4 greater than or equal to x squared. Maybe I'll rewrite it x squared less than or equal to 4. And that basically means that x is going to be between negative 2 and 2. So if x squared has to be less than 4, then x has to be less than 2 on the positive side, but it has to be greater than negative 2 on the negative side to keep the squaring values less than 4. So that's my domain of f. I'm going to hang on to that. I'm going to find my domain of g. Now, g is a linear function, so the domain of g is all real numbers. What I do now is I take these individual ideas on a number line, and I graph them both separately. So I'll take the domain of f. I'm going to have a closed circle at negative 2 all the way to a closed circle at positive 2. And then the function g is all real numbers. And I'll take these two ideas, slide them both onto the number line, and the domain of the sum of functions, the f plus g of x, is going to be wherever the blue and the green overlap. And I think maybe I'll do that in purple here. And they overlap starting at negative 2 all the way until I get to positive 2. And that's going to be the domain of that function. The way I'm going to write that down, just for clarity's sake, I'm going to write the domain of f plus g, then my colon. Instead of just writing d, I'm going to say, what am I finding the domain of here? Because I had several domains going on. So the domain of f plus g is going to be x is an element of the closed interval from negative 2 to 2. So I put those together. And those are the only inputs I can use for that function. That is then, we're done, all right, for that. For the next piece, f minus g of x, once again, similar to what I had before, I cannot put in a value there. So the best I can do is apply the definition and say, well, my f of x is the square root of 4 minus x squared minus, now here's where I have to be careful, since I'm subtracting all of g of x, as I recall, was 3x plus 1. Then I can distribute the negative through those parentheses. You can see if I didn't have those parentheses, I would only end up with a minus 3x and a plus 1, where I want a minus 3x and a minus 1. And just like I did with the sum of functions, there's not much I can do there to simplify, so I actually leave that as my final answer. And I'm not actually even going to calculate the domain of this function, because what I gave for a definition says that the domain for any of the operations above on that first slide are the same. So basically, one way of looking at this, all three of these things are going to have the same domain right there. So once I find the domain of one of them, I have the domain of all of them. So I can just quickly, at the end here, say the domain of f minus g, I'm not doing plus g, f plus g anymore, is going to be the closed interval from negative 2 to 2, because it has the same domain. Let me just check our time here. And the same would hold true for finding the multiplication. f of x times g of x would be the square root of 4 minus x squared times 3x plus 1. And I suppose I could distribute the 3x to, or the square root to both, and have a 3x root 4 minus x squared plus square root of 4 minus x squared. But I'm not sure that looks any better. I'm not sure that's any simpler. And there would be nothing else to do. So I'm actually not going to do that. I'm just going to leave it as is and say, well, that's what the function looks like. It's not the prettiest thing in the world, but that's OK. And then the domain of the function would be, oops, let me write it correctly. So I have the domain of fg, f times g, is going to be the same as it was before. Finally, f divided by g of x, the f of x divided by g of x equals the square root of 4 minus x squared, that's my function f, divided by my function g of x, 3x plus 1. And I now have to look at the domain a little more closely. I've already found the intersection of the two individual domains. The intersection is going to be that closed interval from -2 to 2. But now I have an additional restriction that 3x plus 1 equaling 0 would be bad for us, which means 3x equaling -1 would be bad, meaning x equals -1/3 would also be bad for us. So while at x equals -1/3 is fine for adding, subtracting, multiplying, and dividing, because we can add, subtract, multiply, it's fine for adding, subtracting, and multiplying, because we can do those things by 0. It would be no good here because dividing by 0 would be bad. So I've got to take that intersection, that closed interval from -2 to 2, and throw out the number -1/3. So I would rewrite that, and I would say the domain of f divided by g is going to be the half closed interval from -2 to -1/3, throw out the -1/3, and go until 2 again. So that's all I'm really doing. If you want a visual there, I simply took the idea that we had for our domain and I threw out that -1/3. Let's say -1/3 is maybe right about there. And I threw that out, created an open circle there. And so we don't have to have that anymore. So that's what that idea meant, where we accept where g of x equals 0, because we cannot allow for a 0 in the denominator. So I just had to throw out any values that made g of x equal to 0. All right? So that's how we, according to our list of things to know and list of things to do, find the sum, difference, product, and quotient of specific inputs, find the sum, difference, product, and quotient of functions, and then we found the domain of the sum, difference, product, and quotient. Well, that's pretty good. We just now have to work on the composition function, and we'll be all set. So we don't have too much left here. The composite function f, and that is an open circle there. It's not a multiplication problem, multiplication symbol. That is an actual open circle right in there. And when we read it like this, we read it the composite function f open circle g of two functions f and g is defined as, so when we write the formal definition, we say f open circle g of x is equal to f of g of x. And what I like to think of this as is a chain of events. Whereas with adding, subtracting, multiplying, dividing, we find f of x and g of x separately, then perform the operation to put them together. This is more of a chain of events. And the way I would look at this is if I had f of g of x, order of operations tells you to start inside, which means I start with my x, and put it into the function g. We get some result out. That result is called g of x. And then we take that result and put it into the function f, and we get out our f of g of x. And that's how that works right there. So it's a chain of events. We have to link these two together. And that's composite functions, which we've seen in the past. Now, the domain of the composite function is a bit of a toughie there. So we're going to take a few minutes and definitely talk about that to try to help that out there. All right, let me just make that. I'm going to go a little bigger for emphasis. Okay, the domain of the composite function is going to be the set of all x's, or inputs, in the domain of G. Now here, there's nothing special about G except for the fact that it would be the first function that we would be using in that linking process. So, and that's because, well, we have to get an answer out of G. If x is not in the domain of G, then when we go to here and I try to have an answer here, if I can't get an answer here, if I choose an x that doesn't produce an answer here, well, then I've got nothing to put into f, and I just can't complete the process. So the first thing that has to happen is I have to choose x's that are in G. But then there's an and here. And those x's need to produce results that are in the domain of f. Remember that the output, remember that the output, I don't know what's going on here, the output of the function g, it's a range element for g, but it's a domain element of f. Let me go back to this picture right here. So let's say I have chosen an x well. I've done a good job of choosing an x that does produce a g. That's fine. So that means the first stage of my composition is okay. But let's say that this number, this answer, cannot be put into the function f because it's not in the domain of f. Well, that means I got to go back 2 stages and say, well, I can't use that x. I can only choose x's that get me all the way to the finish, which means I need that x to do 2 things. I need that x to produce a result here so I can get through the function g. And then I need that g to be able to be put through the function f as well. It's a little bit complicated, but we're going to work through that. Let's look at a few examples just to see how it goes. Let me slide that out of the way. So here's our third example. If f of x equals x squared minus 1 and g of x equals the square root of x, find f open circle g of x and its domain. So we would take and we would rewrite f open circle g of x as f of g of x, which really says we're putting the function g into the function f. So the function g is defined as the square root of x. So simply by substitution, that gives me f of the square root of x. I can do that because I see that g of x is equal to the square root of x, so I can make that substitution. Next, the function f, the function f says take its input x, square it, and then subtract 1. Well, now my input into the function f is the square root of x. So this is going to become for us equals the square root of x squared minus 1, which equals to x minus 1. So that's my, if I want to neaten that up, I could just say at the end, f open circle g of x is equal to x minus 1. Now, here's where the domain portion gets a little bit tricky. If I look at my final result, if I look at that final result, and I want to talk about its domain, I would say, oh, it's all real numbers, no problem, because it's a linear function. But it actually isn't all real numbers. remember that this is a composition of functions that came through the square root function. If I erase, let me erase all this stuff for a moment here. Let me see what's going on here. Do a little erasing here. Sorry, kids. We're getting there. All right, let's clean this up. Remember now, this function, g of x, is the square root function. Maybe I can put that on there somehow that everybody will be able to see it. It's the square root of x, which means the x's that go in there can't be negative. They can't be negative. So that's the domain of g. Now, once I take the square root of x and I get these values out of here, I know that all those values of the square root of x are going to be positive. F being linear, being a polynomial, it's not going to be any trouble. Whenever we do this, whenever we work at this, we always take our domains. When we're working with our domains algebraically, take the unsimplified version. Take that part to look at the domain. So I'm going to look at this unsimplified version and say, okay, what would happen here? Well, that means x has to be greater than or equal to 0. All right? And now, so that ends up being the domain of this function. This is definitely a little tricky. We'll do some more work in class with this when you get into class. We just want to give you a few examples. So I'd say the domain of, oops, let me get my colors straight here. The domain of f open circle g is x is an element of the half-closed interval from 0 to infinity. I can confirm that graphically as well. If I take my calculator and I go ahead and I put in the unsimplified version of this. So I'm going to go y equals, and I'm going to go parentheses, square root of x, close the parentheses for my input, close it for my grouping symbol, and I square it, minus 1. So that's that green boxed unsimplified version. I'm going to go with a zoom 6 just so we can look at it. And we can see that the graph does not exist everywhere. It only exists starting at x equals 0. I can confirm that using the trace button. X equals 0, y equals -1. If I hit my left arrow key just one little bit, one button push, boom. My x is -2.11, and I do not have a y coordinate. Look at the bottom of my screen. I don't have a y coordinate, which is telling me that I cannot calculate a y coordinate, which means that x is basically out of the domain. I cannot, that x can't be used to get a y. And then if I scroll to the right, it goes forever. So just a graphic confirmation of the algebraic there. Okay? Let's do one more example here. Just looking at this sort of stuff with the domain and the range. Find g open circle f of x and the domain. So we're going to compose in the other direction. G open circle f of x is equal to g of f of x. By substitution, that means g of x squared minus 1. Let me make sure I remember that correctly. Yeah, x squared minus 1. And the function g was the square root function. So the function g said take the square root of the input. And now that's my input. So it's going to be the square root of x squared minus 1 is going to be this. And this actually can't be simplified at all. Remember, you can't take the square root of a sum or a difference. So final result, g open circle f of x equals the square root of x squared minus 1. And we're kind of stuck there. But if I want to find the domain, I'm going to look at that. Now, what is handy in this particular case is that my unsimplified version could not be simplified. When I look at the function right when I made the substitution, it can't be simplified. So that means I can just work straight off of that, saying, well, x squared minus 1 must be greater than or equal to 0. You know what? I'm looking at this and I'm saying to myself, oh man, that's a polynomial inequality. I can't just add 1 to both sides and take the square roots. I've got to do a sign analysis. Well, that inequality becomes x plus 1 times x minus 1 greater than or equal to 0. And another way of looking at it would be to say, hey, you know what? That's factored form of a quadratic. And we studied this last section. And I would say, hey, you know what? That's simply a polynomial, a parabola, quadratic, with x-intercepts at -1 and 1, and with a positive leading coefficient. So that means it opens up. So this is the parabola that I have there. And I want to know, where is the parabola greater than or equal to 0, which basically means where is the parabola above the x-axis. And where indeed is that parabola above the x-axis? That parabola is above the x-axis here and here. So now I just need to represent that using intervals. The domain of G open circle F is going to be x's on the open interval from -infinity to -1, union with the open interval from 1 to infinity. So I don't really need to do a sign analysis now that I knew something about the graph. Remember, kids, we're really trying to focus on the connection between the algebraic and the graphic. I can avoid a whole lot of nasty algebraic work with a sign analysis if I can think about what the graph means, and especially what the graph looks like, and what that inequality greater than or equal to 0 means. It means where is the graph above the x-axis. So this is my domain. I want to confirm it. I can go to my calculator, go into my y equals, clear that out of there, give me a square root function of x squared minus 1, close my parentheses. I'm going to have a zoom 6 again just to see that. And we can see that this graph does exist from -infinity to -1 along the x-axis, and then it stops. And it starts again at x equals 1. I can confirm that with the trace. If I look at trace x equals 0, y equals nothing. There is no y coordinate. 0 is not in the domain of the function. If I type in 1, hit enter, I get a point. If I go just to the left, and there's nothing. There are no y coordinates between -1 and 1. There's no y coordinates between x coordinates of -1 and 1. And so I have a graphic confirmation of my algebraic work. Okay? Okay, kids, we're going to leave off at this moment here. You have your notes. Come into class with questions. And we'll do, don't worry if it's a little confusing. We're going to do some more examples in class. The next slide has a couple more examples. We'll do those in class together and work through a little more there. But thank you for your attention. I hope that you got through at least the basics with some confidence. Thank you.